Is it possible to determine the empirical formula of an organic compound by simply burning the compound? Well, the answer is yes, but of course you have to do a little bit more than just burn the compound. You have to collect the products that are formed, which are namely H2O and CO2. In this chem activity, and specifically in the teaching model number 1, we will see how to do a combustion analysis to determine the empirical formula of a compound. The intended learning outcomes are that you will be able to use experimental data from a combustion analysis to determine the empirical formula of a compound. Also, given the empirical formula and molar mass for a compound, determine the molecular formula. I'm going to use the example of ascorbic acid, so you'll see that the problem is presented as a question in front of you. I've also made a diagram to show you what the instrument would look like in a combustion analysis. Now my diagram is a little vague, so let me describe to you the parts. Of course, we're going to have some sort of furnace, and we'll put our sample in there. Our sample would either be a powder or a liquid. There would be a stream of oxygen passing through the furnace and over the sample. Therefore, there's an excess of oxygen. We ignite our sample, and any H2O that's produced would be collected by an H2O absorber. This would be some chemical that will bind completely to the water. Any CO2 that's produced would be collected by a CO2 absorber. Again, a chemical that would bind to any CO2 that's produced. By measuring the amount of H2O and the amount of CO2 that's produced, and knowing the original mass of our sample, we can determine the empirical formula. Let me give you a few more details. For one, I'd like you to understand the general reaction concerning this combustion analysis. The reaction looks something like this. In a typical combustion analysis, the organic compound will have a carbon, a hydrogen, and often it will have an oxygen. It doesn't have to. It might have a nitrogen, also it might have a phosphorus. The example that I give here is one that involves oxygen. You can do examples also involving just carbon and hydrogen, and in fact you'll see these are a little easier. The problems involving nitrogen are a little more tricky, and you have to be given additional information. The idea is that this compound of unknown formula is combusted in the presence of oxygen. So we show that as plus oxygen gas. This would go to form, in a complete combustion, carbon dioxide gas and water. Notice that this is not a balanced equation, because I don't know the chemical formula of my original compound. Therefore, this equation cannot be balanced. It just gives you a layout of what's going on in this reaction. Now let's look specifically at the problem. One of the things that I encourage you to do is to pull out any relevant pieces of information. Actually, I'd be very explicit about this so you don't get the numbers mixed up. The first thing to notice is that it's a 6.492 gram sample that's analyzed. So that's the mass of our original compound. I'm going to write out that number right below the formula that I'm using to represent the compound. Notice that a mass of carbon dioxide that's produced is 9.743 grams. Again, I'm going to write that right below the CO2 in my skeleton kind of reaction. Then finally, I'm going to write down the fact that it's 2.641 grams of H2O that's formed. Again, I think this information is vital so you can keep things straight. There's other information that's given in the problem, for instance, the molar mass of ascorbic acid. Of course, this is going to help us translate the empirical formula into the molecular formula. Now there's one more thing that I should mention concerning the skeleton reaction. It's all based on the idea that any carbon that's in our original compound, when combusted, must go directly to CO2. So I'm just going to grab my pen here, and if you've written out the skeleton reaction, you may want to do the same thing. Any of the carbon that's originally present has to go to the CO2. In a similar way, I'm going to grab another colored pen. Any hydrogen that's present has to go to forming the water. Therefore, we're going to use the amount of CO2 that's ultimately formed as an indication of how much carbon was originally present. We're going to use the amount of H2O that forms as an indication of the amount of hydrogen that was originally present. We can't do the same thing, however, for the oxygen, because as you can see, there's oxygen in the CO2 that forms, there's oxygen in the water that's formed, and we don't know where the oxygen has come from. Has it come from the oxygen that's in the compound, or has it come from the molecular oxygen that's in the air? So you see, we have to determine the oxygen by other means. It's not difficult. You just have to take a different approach. This shows you the layout of the problem. Let's now get down to the calculation. As with any empirical formula determination, the steps are to find the mass of each of the elements, convert these masses to the amount of the elements in moles, and then finally to the mole ratio. I've set up a bit of a template on your sheet, and you see something similar here, where we're going to try to find the mass of carbon, the mass of hydrogen, and the mass of oxygen. In previous problems, we found these by using the percent composition and assuming 100 grams, for example. In this case, we have to find the mass of carbon, hydrogen, and oxygen by a different means, based on how much CO2 and how much water was formed in the combustion reaction. Let's start with the mass of carbon. We know that we can find out how much carbon was in our original sample by knowing the mass of CO2 that was produced. So we'll start there. I'm going to make a bit of a unit plan to guide me in my calculation. I know the mass of CO2 that was formed. From there I can determine the amount of CO2 in moles, and from there I can determine the amount of carbon atoms. It's a 1-to-1 mole ratio. And then finally I can determine the mass of carbon. The calculation will look something like this. 9.743 grams is the mass of carbon dioxide that was produced as a result of the combustion. I multiply this by the conversion factor involving the molar mass of carbon dioxide. From there, I'll convert the amount of CO2 to the amount of carbon atoms based on the mole ratio. Finally, I'll determine the mass of carbon that was in our original sample. That is the 2.65902 grams of carbon. I can do a similar analysis to find the mass of hydrogen. The unit plan would look something like this. I'll start with the mass of water that was formed as a result of combustion. I'll convert this to the amount of water. Then using the mole ratio, I can find the amount of hydrogen, and then finally the mass of hydrogen. The calculation looks something like this. 2.641 grams was the mass of H2O that was formed as a result of the combustion. Multiply this by the conversion factor involving the molar mass of water, then by the conversion factor that there are 2 moles of H atoms for every 1 mole of H2O, and then finally multiply by the molar mass of hydrogen. Note that we multiply by the molar mass of monoatomic hydrogen, not the molar mass of diatomic hydrogen, nor the molar mass of H2O. Now I have the mass of hydrogen in the original compound, the 0.295523 grams. Thus far, I have the mass of carbon, the mass of hydrogen. I cannot do a similar analysis, however, to find the mass of oxygen. But if you think about it, we have the mass of carbon, we have the mass of hydrogen in our original sample. The only other component is the mass of oxygen. We also have the total mass of our sample combusted. So we can find the mass of oxygen by subtracting the masses of carbon and hydrogen from the total mass of our sample vitamin C. The calculation would look something like this, where the 6.492 grams is the mass of our original vitamin C sample. I'll subtract from this mass the mass of carbon, 2.65902 grams, that was in the original sample, the mass of hydrogen, the 0.295523 grams that was in the original sample, and that leaves me with 3.53745 grams of oxygen. Now I have the masses of each of the elements that were in the original sample. Essentially, we're at the same point in the calculation of empirical formula where we have found the mass of each of the elements. The rest of the calculation should be fairly straightforward for you. However, we can do it together. Here's a similar sort of table to find ultimately the ratio of carbon, hydrogen, oxygen in the compound. There are always 3 steps in doing this sort of determination. Step 1, find the mass of each of the elements. Step 2, find the amount in moles. And finally, step 3, find the whole number ratio. I'm going to write in the masses of each of the elements that we found from the first part of the calculation. I am then going to calculate the amounts of each. To calculate the amounts of each, of course, requires using the conversion factor involving the molar masses. First of all, the molar mass of carbon, not carbon dioxide. Then the molar mass of hydrogen, that is monoatomic hydrogen, not water. And finally, the molar mass of atomic oxygen, not diatomic oxygen. This allows me to find the amounts of each at this stage. I remind you that I'm not rounding off my numbers. I'm keeping all the correct numbers sig figs. You'll see that if you round off too soon, you may end up with a whole number ratio that is difficult to interpret. It's a good idea to keep as many significant figures as you should, and then you see I'm even keeping some additional digits, so I don't have to round off too soon. Finally, the last stage is the whole number ratio, and this involves dividing by the smallest amount. Now in this case, the amount of carbon and the amount of oxygen are essentially identical. Oxygen's a little bit less, and I'll divide by that, but I could have used either one. We can see the whole number ratio for the carbon compared to the oxygen is roughly 1. The whole number ratio for the hydrogen is 1.326, and the whole number ratio for the oxygen, of course, is 1 because I'm dividing by that amount. When you get a fraction like this, or something that involves a decimal point, like 1.3, hopefully you'll recognize that this is essentially equivalent to 1.33. And that signifies to me that I need to multiply all of these numbers by 3. For instance, if you had arrived at 1.25, you'd have to multiply everything by 4. If you get 1.5, you'd have to multiply everything by 2. So here we multiply everything by 3. Therefore, in terms of the ratios, I've got roughly 3 carbons to roughly 4 hydrogens to 3 oxygens. Putting this together as an empirical formula, therefore, C3H4O3. That's the empirical formula for ascorbic acid. Finally, as we've discussed previously, in order to determine the molecular formula, you have to pay attention to the molar mass. I also need to calculate the empirical formula mass, essentially just the molar mass for the empirical formula. I divide the molar mass by the empirical formula mass. Note that the empirical formula mass should be equal to the molar mass or smaller than the molar mass. If you have obtained an empirical formula mass that's bigger than the molar mass, something went wrong. Not only should the empirical formula mass be equal or smaller, the calculation should result in some sort of integer ratio. In this case, I end up with the ratio of 2. Now we multiply the empirical formula by 2, and finally I end up with the molecular formula. These are the steps in determining the empirical and molecular formula from a combustion analysis. I hope you see that it's really only the first part that's a little bit different from the original empirical formula determinations. But I'm also hoping that you feel that you have the tools to complete this sort of calculation.